Okay, this is video 1 for the Ohm's Law unit notes. In this unit, I want you to be able to solve problems using Ohm's Law. I want you to solve problems involving electrical power and understand what voltage drops are. Okay, so let's go ahead and get started. We've discussed in previous unit about circuits, and an electrical circuit is formed when we have a conducting path, such as a wire, that allows those free electrons to move continuously. Now, the movement of electrons through a path is what we call current. It's often referred to in terms of flow, just how water flows through a pipe. The force that motivates electrons to flow through a circuit, this can go by two names. Commonly, it's called voltage, but sometimes it's called electromotive force. There is a difference between these two, and it's something we'll discuss when we talk about batteries later on this year. So this voltage, or this electromotive force, it's a specific measurement of the potential energy that allows relative motion between 2 points. So when we talk about voltage, we're referring to how much potential energy exists to move the electrons from one point in a circuit to another point. The free electrons, as they move through materials, we can kind of think of them encountering a little bit of friction. And this opposition to motion is what we call resistance. So the amount of current in a circuit, it's going to depend on the amount of voltage available to motivate the electrons, but it's also going to depend on the amount of friction that opposes their movement. So let's put all this stuff together then. Current. We use the letter I for its symbol. That's because when early scientists were studying current, they thought of it in terms of intensity, how intense the flow is. The unit is the ampere. And the abbreviation, I've seen it both capital A or AMP. I've seen it written both ways. The voltage, we can use a symbol for EMF. It's kind of like this E-looking symbol, or a V. Its unit is the volt, and we abbreviate it with a capital V. And finally, resistance, its symbol is a capital R. Its unit is the ohm, and its abbreviation is capital Omega. So the horseshoe-looking Greek letter. Each unit of measurement then was named after famous experimenters in electricity. So the amp after the Frenchman André Ampere, the volt after the Italian Alessandro Volta, and the ohm after the German Gregor Ohm. Now, with all this, we can now write out Ohm's law, which simply says that the voltage equals the current times the resistance. I would argue that this is one of the most important models or formulas of our modern times. This is used in everything. So let's take a quick example of this. Here we have a circuit. The battery has an EMF or voltage of 12 volts. We have a lamp in our circuit, resistance of R, and what we want to do is we want to find the current. Now, the current traditionally flows from the positive terminal back to the negative terminal. The way we originally defined current was the path that a positive charge would flow. However, we know that the electrons are actually going from the negative terminal to the positive terminal. That stuff's not too important. So let's calculate how much current is in the circuit. So Ohm's law says that the electromotive force equals current times resistance. So that means we've got 12 volts equals current times 3 ohms. So the current then will equal 4 amps. Pretty simple. Expect me to ask you questions about calculating currents, calculating voltages, or calculating resistances. And basically, I have to give you 2 out of the 3. And using Ohm's law, you can find the last one. All right, moving on. Another important term is electrical power. So this is in addition to voltage and current, another measurement of the free electron activity in a circuit is called power. Now we need to begin by first understanding, what exactly is power. So a definition, power is the rate at which one form of energy is converted into another. In previous lessons, what I showed you was that power equals work over time. So another way of looking at it then is power equals energy divided by time. And this is really how I want you to think about power. It's energy over time. So if we take a look at the power of a car, and we measure that in the United States in horsepower, the horsepower of a car, it does not tell you how steep of a hill the car can climb or how much you can tow with the car. Both of those are work. Climbing a hill, that's a force over a distance. Towing is a force over a distance. So that's work. So what the power does tell us is how fast the car can do those things. So the higher the horsepower of a car, the faster it can climb a hill, or the faster it can change its velocity, which means that the faster it can tow. So what power tells us is how quickly something converts one form of energy into another form. So for a car, power tells us how quickly the chemical energy in the gasoline is becoming kinetic energy of the car. So the higher the horsepower, the quicker the car's engine can convert that chemical energy into kinetic energy. So back to electrical things. Resistors, this is what they do. They convert electrical energy into heat energy. And the way we can calculate this power, one of the ways anyways, is that this electrical power equals a current times the voltage or electromotive force. There's also a quick little conversion here. I got this backwards. Cross this out. 1 horsepower equals 746 watts. And watts are the unit of power. All right, so taking a look at this right here, this is our, we call this the electrician's wheel or the electrical engineer's wheel. What it does is it combines the equation for power and Ohm's law it just puts those together to solve for each one of those 4 variables. So for power, here's one equation, I times electromotive force. Or I can do I squared times resistance, or electromotive force squared divided by R. Here's Ohm's law, voltage equals I times R. Or it can be power divided by I, or the square root of power times resistance, so on and so forth. If you have this wheel, which you can use for quizzes and tests, you can solve for anything. So let's go back to another example here. So we have a circuit where the EMF, or the voltage, is 18 volts. We have a resistor of 3 ohms. What I want to calculate is the current, and I want to know how much power. Better use a P instead of an R. So that lamp is converting electrical energy into heat and light energy, and I want to know how quickly it's converting that energy. All right, so the EMF, this should be pretty easy. Ohm's law says that EMF equals I times R. So I, the current, would equal EMF divided by resistance. And we can see that right here. So that's going to be 18 volts divided by 3 ohms. So that's 6 amps. Now for the power, if I have EMF and resistance, I could use this equation right here. So the power would equal 18 volts squared divided by 3 ohms. And if we do this, we get 108 watts. So this is a 108 watt light bulb. All right, that concludes this video.